This is Discrete Mathematics, Chapter 5, Section 5, Spanning Trees, a video with some audio. Let's see how well this works. Spanning trees. Suppose you have a connected undirected graph. What does that mean? Connected, every node, every vertex is reachable from every other node. Undirected means there's no arrows. You do not have an associated direction. A spanning tree of a graph is then a connected subgraph in which there are no cycles. So this is a graph. It's connected. In fact, it's complete. This is a complete K4. Completely connected, like totally. So this is undirected, though. There's no arrows. How do you get a spanning tree? Remember, a tree can have no cycles, so there are a bunch of choices. These are just 4, and maybe that's all of them. But you can see that none of these are going to give you any cycle at all, and that's what you want. How do you find a spanning tree? Well, pick an initial node, whatever node you want. Call it part of the spanning tree. Usually we call it T. Do a search from that initial node to all the adjacent nodes, adjacent vertices, and add one to the spanning tree, both the node and the edge. And then you keep doing that over and over until you get to all of the nodes. But remember, you got to make sure that you have no cycles in there. So this is one possible, and this is another possible. There can be many spanning trees, but what we'd like to do is minimize those. Like if you're building a set of houses in a subdivision and you want to connect the electricity, the water, the sewer lines, the telephone lines, any other lines, you'd also want to maybe do it underground so it looks really cool. There's no telephone poles and stuff like that. So you better do this because it's going to cost a little bit to dig all those things with a minimal cost. To keep the cost down, you could just use a spanning tree, but of course that may not be minimal. Not all the houses are equal distances apart, so you'd like a minimum cost spanning tree. Well, if you have a connected, undirected graph with a weight or cost associated to each edge, the cost of a spanning tree, any one that you make up, would be the sum of the cost of the edges. The minimal cost spanning tree is, of course, the one that has the lowest cost. So if you took this, we could look at all the different ways to get spanning trees and then add up all those edges and see if we get the smallest or the lowest, the minimum, and this would be it. But you're saying, gosh, I don't see how you got that. Well, just a second. A minimum spanning tree, MST, is a subgraph of an undirected graph such that the subgraph spans, includes all nodes, vertices, is connected, is acyclic, no cycles, and has a minimum total edge weight. There are a couple algorithms, Prim and Kruskal's, that work with undirected graphs. We're going to go through both. They work with weighted and unweighted, but unweighted seems to be not very interesting. I mean, you can do almost anything with that because it doesn't really matter. You'd like some sort of like greedy algorithm that produces optimal solutions. You want to find the smallest the first time. Dijkstra's algorithm is similar to Prim's, or Prim's is similar to Dijkstra. D sub v is the weight of the path, not necessarily the path length, although the length could describe the weight too. So if we start with this graph, if these are all the houses connected and we need them connected somehow, then we would like to come up with this. Now, one thing I want to remind you is there's this edge out here that is 2 that I keep missing when I do this recording. So don't let me miss that. Let me know if I do that. This is how you might initialize things if you were writing a program. But let's start and say D is where we're going to start. T in the K column means that's part of the tree. The distance from D to D is 0. And there is no predecessor with that. The P sub V. So you find all those vertices that are adjacent to D. That's C and F and G and E. And find the minimum weights for those. Well, you've really only got one choice. Those are it. 3 and the 25 and the 18 and the 2. Well, to get a minimum spanning tree, you pick the smallest. So the GD. Put that in your tree. Now you're going to update the nodes, the vertices, because G is now going to be something that can be adjacent. So you've got H, which is 3. You've got E, which is 7. D and E was 25 before, so G and E is better. So E and G is now 7. You've got D and F and D and C, but that's the same. Choose the smallest. Well, you've got two choices, 3 and 3. Which one do you choose? It doesn't matter. We'll choose this first one. So the CD is next. Put that in your tree. Update your nodes. Now you've got adjacency between B and C. You still have the E and G, the F and C, and the H and G. Which one's the smallest? Well, it's still, again, 3's here. We'll choose F. Put that in your tree. Update your nodes. Now you've got A and F, B and C. You've got E and F, and H and G. Smallest is 2. This is the one I always remember or forget. F and E is 2, so that's the next one in there. Update your nodes. So you still got the 10 for A and F, B is still 4, and 3 for H and G. I guess the 3 is the smallest. Put that in the tree. Update your nodes. Now that you've got H, you can get to A with 4 instead of using the F 10. Both the same. Which one you want to choose? We'll choose the first one. Put A in there. And then you update your nodes, which doesn't change the B and C, which is the last thing you'll put in there. So now you've got all these red lines, which is your minimum spanning tree. If you want to see that only, you can get rid of the other edges, and that's how you get to anybody from anybody with the least amount of cost. Sort of interesting. Wonder why this is a 2. For whatever reason, that's going to be one of the cheaper ways to do it. Same as D and G. So, what about our friend Kruskal? This works with edges rather than nodes, which, I don't know, you'll see. 2 steps. Sort the edges by increasing edge weight. Select the first value in these edges that do not generate a cycle. This notation is a little confusing. Let's just do it. You take that same graph, and you take these and say, okay, there's a 1, there's a 2, there's a 3, and a 3, and a 3, and a 4, and a 4, and a 4. I guess there's 4 3s. And a 5, and a 6. Is there a 7 any place? And a 10. I wonder what happened to that 2. Anyway, if you're putting those in order, you have DE is 1, DG is 2, so you just put those in order. These are the edges, DE, DG, EG, and these are the weights from 1 up to 10. I guess we don't have a 7. Now, how do you choose these? Well, you go from lowest to highest. What you want to do is, we're going to start with D again. If what you choose, the next one in the list, if you choose that and it makes a cycle, you don't choose it. So let's start with D. D and E. So that's 1. Can we add DG to that? That doesn't make a cycle. Yeah. Can we add EG? No. That makes a cycle. What about CD? Yeah, we can add that. GH, sure. CF, sure. BC, think so. BE, no, cycle. BF, no, cycle. BH, that's okay. Up, BH. No, a cycle, because I didn't see the CB. How about AH? That should be okay. DF. That will create a cycle. Oh, in fact, we don't need those. Why? Why can we stop? We've run out of nodes. So when you've run out of nodes, you don't need what's left. And if you add all these up, just stop adding when you get to this, 21. Okay.